Yeah.
Yes, you could start.
Okay, good afternoon. Welcome to this third lecture on inelastic neutron scattering and quasi-elastic neutron scattering. Okay, just so what are the things we look at? See, as you said, we have the periodic dynamics and the stochastic dynamics, which respectively are studied using inelastic and quasi-elastic neutron scattering. In periodic dynamics, you have a large variety of phonons. So when you go into details, this could be translations, rotations, rotational vibrations, librations, bond stretching, bond bending, and so on. Now, if one has to selectively observe any specific excitation, then this depends on, or this is characterized by the corresponding eigenvector of the phonon. And as we shall see, the neutron scattering intensity is strongly depend on what the eigenvectors are.
You will know the eigenvectors.
No, we will come to that. Phonon eigenvectors or phonon polarization vectors, something that gives the nature of displacements, of atomic displacements that are involved in the phonon vibration. We'll come into more detail. Stochastic dynamics, on the other hand, this could be fairly complex diffusion pathways or time scales. So then again, this gives the corresponding complex wave vector energy variation of the observed intensity. So this is what we will look at. Now, because of the complexity involved in most of these studies, see, in fact, a long time back, maybe 30, 40, 50 years, when one was interested in phonon, like in phonon in germanium or sodium chloride, a highly symmetric structure, then such a complexity was not there, and one could actually predict what kind of intensity variation one sees in the experiments. However, with more complex materials like even perovskites or high temperature superconductors or organic crystals and so on and so forth, it is essential to have computational models of the dynamics for two purposes. One, to even plan the experiment properly, and then also even analyze the results and draw conclusions out of it. So for that, there are various theoretical methods involved. For the phonons, you have, that's the technique is the lattice dynamics, and there are lattice dynamics models. Some are empirical models, some are based on the ab initio methods like the density functional theory. These are used. And for the stochastic dynamics, there are a variety of diffusion models, and the details can be investigated using the molecular dynamics simulation. So in today's lecture, let us just start with the lattice dynamics theory that is relevant to the study of phonons. Well, in basic lattice dynamics theory, there are certain approximations, and it is actually under only those approximations that one can talk of concepts like phonons. As you already know, that phonons are nothing but the quanta of the energy of atomic vibrations. So the vibrations of atoms in the solid are said to be quantized under certain conditions, and these quanta are called phonons. So they have a distribution in terms of the wave vectors and energy, and a large number of excitations depending on the number of atoms involved in a primitive unit cell, the so-called number of degrees of freedom. And now let's see what are the approximations that are required for ensuring this, because this kind of independent phonons or the so-called normal modes have certain requirements. Okay, so the first approximation is what is called the adiabatic approximation. This is very important for the study of phonon excitations or lattice vibrations or even the electronic structure. The main idea here is separating the crystal potential between nuclei and electrons. As we know, there is a large difference between the mass of nucleus and the mass of electrons, and consequently, the time scales of the dynamics are also very different. Nuclei move much more slowly than electrons, and so in a way, in most cases, one can say that the electrons essentially follow adiabatically the nuclear motions because nuclei move very slowly, and the electrons can quickly adjust to whatever slow movements the nuclei have. So, incidentally, the nuclear motions are, as we saw in the previous lectures, is in the range of picoseconds to femtoseconds. And so electrons and the corresponding energies are in milli-electron volts, whereas electronic energies are usually much higher, electron volts and so on, and higher. So that's some orders of magnitude more. Of course, there are exceptions, but right now we'll not deal with that. So the adiabatic approximation is essentially, in this context, the crystal potential can be expressed in terms of nuclear coordinates alone, and the electrons essentially follow the nuclei. So effectively, the nuclear potential includes contribution from the electrons. In fact, we know that when two atoms interact, the interaction is largely between electrons. But however, this can be effectively written in terms of as a function of nuclear coordinates. So that's a very general approximation that separates out the nuclei with electrons. Then there is another approximation that is specific to the concept of normal modes or phonons, and that is what we call the harmonic approximation. Here, at low enough temperature, the amplitudes of atomic vibrations are fairly small, and therefore, the displacements of atoms during vibrations being small, the potential energy can be expressed in only up to second order in the displacements. Okay, so if the potential energy can be written up to, with only second order in displacements, like for example in a simple harmonic oscillator, you have a simple harmonic oscillator and we write the potential equal to say half kx square. Okay, so k being the force constant, x being the amplitude. So that's how. So it's first order term is not there because at equilibrium, the first order term goes to 0. So around the equilibrium, the minimum order term is the second order term. And once that is so, and the higher order terms can be neglected, then as we will see, it's possible to simplify the problem of the atomic vibrations in such a way that vibrations, the total dynamics becomes essentially a sum of a large number of simple harmonic oscillators, which can be called, and the energies of those simple harmonic oscillators are quantized, and so they can be related to the phonon energies. Okay, so in a way, what we say is under the harmonic approximation, the vibrational part of the dynamics can be expressed as a sum of a large number of simple harmonic oscillators. So each of these are like normal modes which don't interact with each other. They can be viewed independently. So, and so then we have this concept of phonons. I am not going to go into a lot of further detail into it because presumably you already know about it or one can study it separately. But here it is sufficient to say that the dynamics at low temperature specifically in a periodic crystal can be thought in terms of normal modes or phonons. In fact, you don't really even have to think of a periodic crystal. Even if you have a molecule, then the vibrations, the internal vibrations of the molecule at low enough temperature can be like can be viewed in terms of this independent simple harmonic oscillators. And again, those vibrations are quantized, and you have definite vibrational frequencies in case of an independent molecule, and so also in a crystal. Then there is a variation of the harmonic approximation called the quasi-harmonic approximation. Here, unlike in the harmonic approximation where the energy is expressed about the minimum energy structure, so minimum of the energy with respect to all the atomic coordinates as well as lattice constants and so on, so that there is no external stress on the crystal. The external stress is zero, and internal forces on the atoms are also zero. So with that, around that such a minimum energy structure, if you expand the potential energy, then that is called the harmonic approximation. However, if you wish to calculate it at a different volume or different pressure, which means we may have some external pressure on the system, on the crystal, a finite pressure, not necessarily zero, and correspondingly the volume will be different, or even if it's not a cubic material, then the lattice constants A, B, C, alpha, beta, gamma, they can be different from the minimum energy structure in such a way that it corresponds to certain pressure, positive or negative. So what I mean is there are no anisotropic stresses inside, but again, the internal forces on atoms have to be zero. So the calculations are performed at any structure that may not be at the minimum energy. However, it should correspond to in some consistent manner corresponding to certain pressure. And about that structure, minimum energy structure, about that such a structure, if you expand it further, then you will get the corresponding phonon frequencies which are different from the harmonic vibrations, harmonic frequencies. But however, then they may correspond to the specific pressures. So in a way, the change in the frequencies as a function of volume or pressure can be calculated under the quasi-harmonic approximation. We still assume that the temperature is low, such that the higher order terms in the expansion are negligible, and so in a way the vibrations are still small enough. If there are further higher order terms, there are usually perturbation methods, or which can give you further variations of the frequencies as a function of temperature and so on. However, in that case, strictly the phonons are not all non-interacting or independent of each other. There are also phonon-phonon interactions, and once you have interactions between phonons, that can give rise to some kind of decay of phonons or certain lifetime of phonons. And so these are the characteristic quantities. Again, those can be measured by experiments. You can measure for example, how the phonon lifetime changes with temperature and other parameters. We have a book published about 10 years ago, and where we have discussed a lot more about these kind of things and its relevance to thermodynamic properties. Okay, so let's get into a little bit of theory relevant to what we just discussed. So for that, let's just define the positions of atoms. Now, what are the numbers here? L and K. So any atom in the crystal, the atom can be defined or characterized as the atom inside one primitive cell, and then the index of the primitive cell. So if K is K is the atom inside a primitive cell, and K goes from 1 to n being the number of atoms in the primitive cell, and L is another index, which is actually a three-dimensional one, because in 3 dimensions you have along, let's say, the 3 orthorhombic directions, or three lattice vectors along A, B, C. you can have L1, L2, L3 that will define which unit cell one is talking about. So for such an atom, let's say this is the equilibrium coordinate R of L and K, the kth atom in the Lth unit cell. And so that's the equilibrium value. About the equilibrium value, there is a small displacement characterized, which identifies what is the vibration, and that is the net coordinate. Okay, so this is a function of time. U is a function of time. R is the equilibrium position, and that's the position. Now, so this is we have to define these notations. Please don't confuse K with the wave vector. K here is just the atom number. K wave vector as we use in neutron scattering, so that's different. Okay, so now because of the crystal periodicity, any solutions of the dynamical problem normally would have such an expression. What essentially we are saying is that these displacements as a function of time should have some term which is independent of the unit cell. So this is the basic amplitude, and then there is a phase term, and Q being the wave vector of this vibration. Okay, so the vibration that we are talking about has a wave vector Q and a frequency omega. Omega is again a function of Q, and R is the equilibrium distance from origin, or equilibrium vector from the origin. So that is the phase term, and that is the amplitude of this. So this is that's a vibration. That is the kind of solution one tries, and that is essentially making use of the fact that we have a periodicity, and the periodicity essentially comes in this phase vector. Okay, so if we have such a phase equation, such a displacement equation, then it's possible to write the equation of motion. So I am skipping here all the details. You write essentially the Hamiltonian of the total kinetic and potential energies, and then you put in, assume this kind of a trial displacement or displacement. So then there is the equation of motion comes out to be like this, which is it's very similar to what you have in a simple harmonic oscillator, but here it's not a single simple harmonic oscillator. As we will see, it's a large number of them. So m is the mass of the atom K in the primitive cell. U is the amplitude for this vibration, omega square, and this is all the important terms involving the interaction between atoms come in here. And this is what is called the dynamical matrix term here, and which is so this equation of motion essentially connects the amplitudes of amplitude for the atom K in a direction alpha. Alpha is the direction here, which can be along one of the three orthogonal Cartesian axes. And these are the corresponding amplitudes for all the other atoms in the primitive cell. Okay, so that's the atom K, and there's all the other atoms, including K. So how these are connected? They are connected through the dynamical matrix. And the dynamical matrix, now alpha beta is the two Cartesian coordinates for the vibration of atom K and atom K prime. Q is a wave vector, and this is the force constant. This is the force constant tensor between these two atoms, Lk and L prime K prime, and that's the force constant tensor. It's a 3x3 matrix, and alpha and beta go from 1 to 3 or x by z, and that is the phase term. So I've jumped here a lot. What essentially I'm trying to say is that there are trial solutions for the displacement, and assuming these trial solutions for a harmonic dynamics, you have the equation of motion can be written in terms of the frequencies and the amplitudes, and then the interatomic terms, interatomic interactions are they come through the interatomic force constants, and when such a dynamical matrix can be written down, this is what one will require to calculate. Then if you diagonalize this dynamical matrix, you can get the eigenvalues and eigenvectors, which will correspond to the frequencies and these amplitude terms. So okay, so one has 3n eigenvalues and 3n eigenvectors corresponding to the n being the number of atoms in the primitive cell. So you can say that 3n is the number of degrees of freedom for the atomic vibrations in the primitive cell, and corresponding to the 3n degrees of freedom, you have 3n eigenvalues and 3n eigenvectors. The eigenvector, okay, so the eigenvalues correspond to the square of the frequencies. Okay, that's these numbers. And the eigenvectors will be proportional to these terms, but there is a difference here. There are essentially some proportionality terms which are required between the actual displacement, for example, temperature or various other things. So the basic eigenvector, which is a normalized quantity, okay, so to say you have the dynamical matrix can be shown to be Hermitian matrix, and the Hermitian matrix then has real eigenvalues, and one can write down the eigenvectors which are normalized. So you can find, you see that the eigenvalues have to be positive. So the omega square is positive, but omega, when you take the square root of this number, sorry, omega square has to be real, not necessarily positive, I'm sorry. So there's a real number. If it's positive, then you have the omega j would be real frequencies, which will correspond to a stable, dynamically stable structure. However, if through calculations you end omega squares which are negative, then that would mean that the omega j are imaginary, and that essentially means that if omega j is imaginary, then such a solution is not a periodic solution, but a function that decays with time. So that will not be a dynamically stable vibration. This kind of things happen if you do a calculation in a structure which is not dynamically stable at low temperature, maybe because of possible phase transitions or for any other reason. That has some physics into it, but let's assume that for stable structures that occur at low temperature, these would be then necessarily positive. Now, what are the eigenvectors? Eigenvectors here, J, as I said, it goes from 1 to 3n. So in fact, this essentially corresponds to k going from 1 to n and alpha going from 1 to 3. That is the 3 Cartesian coordinates, and k is the atom, so that's the n number. So now 3n are just the degrees of freedom. One can say that J equal to 1, 2, 3. Okay. So this could be listed that for okay. So now this is of course this J is the corresponding eigenvalue and the corresponding eigenvector. Now, but this vector itself, eigenvector itself, is a 3n dimensional vector. Okay. So these 3n dimensions of the eigenvector just gives us the displacements of all the n atoms in 3 directions. So this is a pattern of displacements of atoms in a particular mode, let's say the jth mode of vibration. In that mode, there are 3n possible displacement values for three values for each of the n atoms, and that 3n dimensional vector is the eigenvector, and J also runs from 1 to 3n. So this relation then omega equal to omega jq, that is the frequency is expressed in terms of the wave vector as a function of the wave vector for these different 3n phonons for each wave vector. This is called the phonon dispersion relation. And now if you plot it, for example, here just a plot for the Q. Okay, so now the Q, the wave vector is a vector in the reciprocal space in the Brillouin zone. So in the Brillouin zone, you can have, you can take any particular direction, for example, say 1, 0, 0 direction, and the Q may go from 0 to 1 or 0 to half or from 0 to the zone boundary, wherever it is. Similarly, there are other directions, 1, 1, 0 direction or 1, 1, 1 direction or any other direction inside the Brillouin zone. But if you, it's a convention to plot it, for example, it's a nickel happens to be a cubic material. So we just plot along 1, 0, 0 direction, 1, 1, 0 direction and 0, 0, 1 direction. And there is only one atom in the primitive unit cell. So then there are essentially only 3, if there is only one atom in the primitive cell, then J goes only from 1 to 3. And there are 3 phonons for every wave vector. But it so happens that out of the 3 phonons, 2 are degenerate, which means the 2 phonons, this is, as you probably know, the longitudinal and transverse phonons. What a longitudinal phonon means is that the vibration is parallel to is along the direction of the wave vector. So if Q is along 1, 0, 0, 0, 1, 1, 0, 0 direction, then that is, let's say, the x direction. Then if the vibration is also along the x direction, then that is the longitudinal phonon. And that is how the frequency changes across from the zone center to the zone boundary. The other 2 phonons which are degenerate are transverse phonons. And here the displacements are along, let's say, the y and z direction. Now, because of the symmetry, whether the displacement is along y or along z, because of the symmetry of this cubic crystal, you have those 2 frequencies are identical. So you don't have you have only 2 frequencies here. However, in the 1, 1, 0 direction, you have 3 separate frequencies. So the longitudinal phonon and the 2 transverse phonons, they are different because the corresponding directions are not equivalent. Again, in the 1, 1 direction, you have the longitudinal phonon and the 2 transverse phonons are degenerate. Here you can also see that these are all called acoustic modes. Acoustic modes are those modes which are, okay, as the name goes, it is related to the sound waves. And here the main characteristic is that at 0 wave vector or the long wavelength, the wave vector is 2 pi divided by the corresponding wavelength. So if Q equal to 0, that means the wavelength is infinity. And at infinite wavelengths, we have 3 modes which have 0 frequency. Now, what do you actually mean by it? Infinite wavelength means all the atoms in the crystal, they're moving, their vibration is identical. Okay, so there is, and if that is the case, then if all the atoms move by identical amount, there will be no restoring force on any atom, and there is therefore the energy of such a vibration would be 0, and that is how they become the 3 0 frequency modes corresponding to vibrations along, say, the x, y, and z directions, and these are the acoustic modes. If you have a large number of modes, then all the remaining modes are called the optic modes, 3 and minus 3. And here's another example, zirconium, which is a hexagonal structure and has 2 atoms in the primitive cell. So now once there are 2 atoms, there are 6 phonons at every wave vector. So there are 6 different branches or 6 different curves plotted here of the dispersion curve. And now again in 3 different directions, you can talk about it. This is, of course, 110 direction. This is a direction in the hexagonal plane, AB plane. 100 is in the let's say A direction in the, or A star direction, there's a reciprocal lattice. ABC is the direct lattice vectors, and A star, B star, C star, we say is reciprocal lattice vectors. So here when we are plotting the wave vector, we are plotting in terms of the reciprocal lattice vectors. So this is again a 1, 0, 0 direction in the hexagonal system, is in the hexagonal plane, and 0, 0, 1 is perpendicular to the hexagonal plane along the C direction. And again, the symmetries are different. So here we have degenerate modes for the transverse modes, and non-degenerate longitudinal mode. So in fact, here, this is a longitudinal mode, transverse acoustic mode. That's a longitudinal acoustic mode. And these two modes turn out to be longitudinal optic and transverse optic modes. Okay, so in this course on inelastic neutron scattering, we will not go into a lot of detail of lattice dynamics, but the idea here is that we have introduced that there are 3 n eigenvalues, there are 3 n eigenvectors corresponding to each of the eigenvalue there is an eigenvector, and corresponding to each eigenvalue the eigenvector is a 3n dimensional vector which gives all the 3n displacements that correspond to this particular phonon. So for example, if you take a phonon here, it will have a eigenvector which is a 6-dimensional vector, and the 6-dimensional vector, the first 3 terms will give the displacement of the first atom in the primitive cell, and the second 3 components will give the displacements of the second atom in the primitive cell, and so on. Okay. Now, okay, I mean, I think what I wish to say is if you have questions or doubts, we can look at that during the tutorial or in any other lecture. So if you have questions, please let me know. Okay, so here, we just showed fairly simple structures like nickel or zirconium. Incidentally, these curves are experimental, these points are experimental data, and these are some calculations done a long time back, which don't exactly accurately fit the experimental data, but which is a very simple calculation with some limitations. So don't worry about it right now. So, okay. Now, this is a more complex material of practical importance. It's a mineral zirconium silicate. And here I just wish to say that there are large number of atoms in this structure. And because of that, it has a large number of phonons. And so this was a very involved exercise of measuring these detailed phonons, phonon dispersion curves along different directions. Here, these measurements are what are shown here are along 100 direction, 001 direction. Only 2 directions are shown here, and and there are a large number of phonons, and they cover a very large range of energies. In fact, it's fairly rare to get extensive measurements of all kinds of phonons in complex materials. Usually one is interested in specific phonons because this takes a much longer time. And here this exercise was completed at 4 different laboratories. Certain low energy phonons could be measured at the Bhabha Atomic Research Center in Trombay. Then based on that, the theory was developed or refined better. And then further, the next set of experiments were done at the spallation neutron source at the Rutherford Appleton lab in United Kingdom. So this is another set of data. And even that had some limitations. One could not really complete all the measurements because of the specific reasons. We'll see what this might be. Then again, These were really completed at the high flux reactor in France, a laboratory LLB reactor, and so in fact this at Trombe and LLB, these are reactor-based triple axis neutron spectrometers, what we just discussed last time. So in triple axis spectrometers, you measure each point separately. So each point is measured in a independent run, which will last certain amount of time. And then, however, ICIS is the at the Rutherford Appleton Lab. It's a spallation neutron source. So the techniques use spallation neutron source is a pulse neutron beam is what you get there, and the techniques used are time of flight methods. In the time of flight method, you can measure a large number of phonons in a single run, but however, you cannot necessarily measure each and every phonon that you are interested in. So it's again, it depends on the technique. Nowadays, things are improving, and you can cover more and more depending on the geometry. But yes, so these are not done each point, but then a single scan gives a number of points and so on. So now to do such a thing, one needs to really develop the lattice dynamics models or the theory better. And in fact, these calculations are, there are a variety of different kinds of calculations are done from empirical models to the density functional theory. Okay, so now there's other thing that you can look at it is if you have the dispersion curves, and we can define the phonon density of states, which is just the total number of or how the phonon what is the density as a function of omega. So say g omega d omega is the number of phonons or eigenstates in a frequency interval omega to omega plus d omega. Okay, so if, for example, the typical dispersion relation is like this, you have the acoustic modes and the optic modes, then the corresponding density of states would look something like this, that you have fairly low density to begin with, but wherever these branches tend to be relatively flat, you get a higher density, because then there are more number of frequencies or more number of phonons in the larger in a larger part of the Brillouin zone. For example, here in so much of Brillouin zone, you get the same frequency. So then you end up getting a peak. And here the wave vectors are then far apart. The frequencies are varying. So this again, I will not go into further detail here. But what I wish to just say is that the density of state it starts from 0, and it depending on the system, typically it goes as omega square, then it peaks, and then these peaks are sometimes called the critical points, where you get fairly high intensities. These have some relevance, and you may or may not have separate structures from acoustic or optic modes. If there are no band gaps, then you may not have a band gap here, but the density of state is there. So unlike the detailed phonon dispersion curves, the density of states are easier to look at, and these are very useful to calculate many of the thermodynamic properties of the materials. Here, this is the total density of state, but one can do you can look at the partial density of states due to each atom. So as I said, you have the eigenvector component, which has components from all the atoms. And so for each atom, if you take the corresponding eigenvector and take this as a weight for the density of state, then you will get a density of state which is the component from that particular atom. So these are partial components of the density of states in the total density of states. Yeah, as you might know that typically we have if there are heavy and lighter atoms, then heavy atoms tend to have low frequencies, and the lighter atoms tend to have the higher frequencies. You also know that in the acoustic modes, all the atoms move in phase near zero, and the atoms move out of phase with respect to each other in the optic modes. So this again another well-known nomenclature. Okay, so now just this is only a formal way of expressing that if you have the collection of all the frequencies as a function of wave vector, so then this means these are all the phonon excitations, and when you have collection of all the excitations, one can do the statistical mechanics, write what is called the partition function in terms of the total Hamiltonian, and which can be expressed in terms of all the frequencies and the total potential energy term. So that's a potential energy term, and that's all the vibrational term. Now this is just only a formal way of essential to say that one can write it formally. And once you have that, then it's possible to write by differentiating the partition function, the Helmholtz free energy. So this quantity is of interest for any further calculation of thermodynamic properties. So let's see what are the components here. You have the potential energy at equilibrium, which is essentially a function of volume or the specific lattice constants. Then you have this the term coming from all the frequencies. Here, I'm sorry, there's a mistake. H should have been H cross, but this is again some software issue. So you have the temperature and the frequencies together. That gives all the free energy contribution to the Helmholtz free energy. And for each mode, for each frequency, then it is weighted by the corresponding density of states. So you can see that once you have the density of states available, for thermodynamic properties, you don't really have to worry about the details of the eigenvector of that mode. Whatever the mode is, the phonon is treated as an independent entity. It's just a quantum of vibration. And the quantum of vibration for this simple harmonic oscillator is all that matters, and you can write the free energy. However, that's remember that the approximation of the harmonic approximation is still very much relevant here. So this is truly valid only under the harmonic approximation. But see, even though we said for the harmonic approximation the vibrational amplitudes have to be small, so that third order terms are not important. But in practice, it doesn't have to be extremely small. In such a, what it means is that up to fairly high temperatures, these theory works well, and if you use it to calculate various other quantities, we get a fairly good agreement with experiments, which means that the higher order terms in the potential energy, which we neglect, are not too large. Okay. So the vibrational entropy can be written. This is important for discussing phase transitions and so on. Again, H should have been H cross. Okay, then you can also write the total energy of the crystal. So don't confuse with the neutron energy transfer. We are talking about lattice dynamics. The total energy of the crystal is the potential term plus the phonon term. So each phonon has a energy, average energy n plus half h cross omega, and n is the Bose population term for this phonon excitation, and so you n plus half h cross omega is the energy of this harmonic oscillator multiplied by the density of states, and the temperature derivative of it gives you the specific heat. So it comes in an expression like this. Now, just one again little thing here. Okay, see, you have all heard of, for example, the Debye model of lattice vibrations. The Debye model essentially assumes that omega is linearly just proportional to q. So it's approximated by a straight line. So all these modes which you have are approximated by a straight line, and then the slope of and the cutoff of that, the maximum frequency then corresponds to the converted into temperature units, gives you the Debye temperature. The good part is that that number, if you have a straight line here, the number which you get at the zone boundary corresponding to the maximum frequency, some effective number, because zone boundary is along different directions may be different, but a typical number gives a good indication of the order of magnitude, or rather better than that, good indication of the average frequency cutoff. And that is useful for many of the experiments where you don't really need all the details of the phonon spectrum, but a single representative number like the Debye temperature is good enough. In case of specific heat, we know that specific heat is zero at zero temperature, then it increases slowly, and then as a T cube as a function of temperature, and then saturates at some number at what is called the Debye limit. So somewhere there is a Debye temperature in the process. Okay. This is just one specific example of a thermodynamic property called thermal expansion. So again, these will not go into details. This arises from enharmonicity of phonons, but this enharmonicity can also be partly derived from the harmonic or quasi-harmonic phonons. See, as we said, there is a quasi-harmonic approximation which can give us how the frequencies will change as a function of volume. So that variation of phonon frequencies as a function of volume can be calculated in the quasi-harmonic approximation, and that variation is expressed as a Gronasian parameter, how the frequencies change with volume. And actually, with not a very difficult theory, it's possible to write down how the thermal expansion depends on these Gronasian parameters, or which essentially has the enharmonicity. So this again, a lot of work has been done. Here, sometimes it's very important to have the variation or the Gronasian parameter of each and every phonon separately, because it's possible that a very small number of phonons have a very large enharmonicity, and that is very important to understand how the specific anomalous expansion occurs. So normal expansion is positive, but then number of solids have anomalous expansion, including negative expansion and so on. Okay. So we have looked at lattice dynamics. One more thing I just wish to tell. There are a variety of phonons. Typically, you have high energy phonons which come from very strong bonds, strong covalent bonds. Then you have medium energy phonons which correspond to not just the stretching modes, but also various kind of lattice modes. And they change significantly as a function of pressure and temperature and so on. And therefore, they govern the elastic or thermal properties. In addition, we also have sometimes, not always, very low energy phonons which tend to zero and has a strong dependence on temperature and volume. And so once the frequencies are very small, and they give rise to very large vibrational entropies, and therefore they have a very important role in anomalous thermal properties and phase transitions and so on. Okay, we'll probably close here. We'll go into the experiments in the next talk, or let me just briefly say the theoretical part here. Okay, so as far as experiments go, we'll just have a preview of a little bit what we are going to do next time. Experiments for phonons can be done in two different ways, using single crystals or using polycrystalline samples. Single crystals can give you detailed information about the dispersion curve, that means the frequency of each and every phonon as a function of wave vector. These are large number of phonons. But then these require, because you have to define a vector inside a solid, inside a lattice, you need a single crystal. And typically fairly large crystals are required, which are not easily available. So these experiments are then limited. You need something like a cubic centimeter, but on a very high flux or high neutron intensity source, you can probably do up to a smaller than this, about 1/10 of it, maybe 100 cubic millimeters or so on. But typically, you need better to have something like this. On the other hand, you can use polycrystalline samples, and you need larger amounts, but then you can measure the phonon density of states. And then this is quite useful also to study various kinds of thermodynamic properties in the solid as a function of pressure and temperature and so on. Now there are, of course, this is just probably a repetition. There are a lot of challenges here. As we said, single crystals are rare, but powder samples, although you can do the density of states, but you require much higher energy resolution than what you require with a single crystal. It is same way as in diffraction. If you do a single crystal diffraction, you measure only one reflection at a time, and therefore you don't need extremely high resolution. However, if you are working with a powder sample and you're trying to do the powder neutron diffraction or powder X-ray diffraction, you need very high resolution because you have to resolve neighboring peaks. And so also with powder samples for phonon density of states, you need a much better resolution, and consequently, and also you need very high intensities. So these are available then only at a few neutron reactors or spallation neutron sources. And now once, because this is a very average information of phonon density of states, as we already discussed, we need computational models. And magnetism, so far we have not discussed, but magnetism we can study independently, but at the same time, the magnetic interactions between atoms will also affect the phonons. So those need to be considered. Okay, as far as the theory goes, this is just a summary of various kinds of theoretical calculations which are done. You can do the free energy minimization as a function of pressure or volume, or use the enthalpy. You can do all this lattice dynamic simulation to obtain vibrational and thermodynamic properties in the quasi-harmonic approximation. Once the temperature is not low enough, then there's another technique called molecular dynamic simulation, which we'll talk about in a future lecture. This technique can be used for periodic dynamics as well as stochastic dynamics. So you can use this also to get the detailed phonon dispersion curves and density of states, and also which will take fully into account the enharmonicity, not limited by the harmonic approximation, and can be more accurate in terms of high temperatures. This also has some limitations. We'll talk about it at that time, but then these are very important to deduce high temperature properties like diffusion and so on. And with the various results, one can study the structures as a function of pressure and temperature, various kinds of long range order and short range order, phase transitions, and so on. Okay, so I think I'll stop here. Then in the next lecture, we'll start with the neutron scattering, detail of the experimental techniques of these various things. If you have any questions at this stage, please let me know. Good. So you can close. Anyway, thank you. So see you day after tomorrow.